Hello everyone. Today we're doing lesson 12.6, which is spheres, surface area and volume of spheres. I actually like this lesson a lot. I think it's relatively simple, so I hope you do as well. Let's go ahead and get started. Now, much of this vocab probably will look very familiar, if not completely the same, except that it says sphere and not circle. However, I am going to draw your attention to the picture and explain a little bit. If you need to pause the video to finish copying in the vocab words, go for it. Please write down whatever you don't know or aren't confident on. Now, drawing your attention to the picture, as you can see, all of these vocab words we were familiar with during circles still apply. So the radius is from the center to the edge, and it'll be the same all the way around the sphere. Chords still have two endpoints inside of the sphere, right there and right there. The diameter is still going all the way across the center of the sphere, and tangent is still on the edge. Okay, so all of these words we dealt with circles still apply to spheres. Now, here are the vocab words you probably don't know. The great circle is up first. The great circle is this circle right here. All right, it is the circle that is in the middle of the sphere. So think the equator of the Earth. That would be the great circle of the Earth. Okay, so it's in the middle of the sphere and it has the same radius as the sphere. And that's what's really nice about the great circle is the radius is the same. And so we can use that in some problems to go back and forth. Another fact about the great circle is, let's take this center of the small circles and then the center of the great circle. This line right here is perpendicular to the radius of the small circle. Okay, so if you have the radius of the small circle, it is perpendicular to the bit of the diameter that is going straight down all the centers. And so what happens is some of the problems will deal with this right triangle right there. And so we'll actually deal with the problem a little later, but it's where you have the radius of the small circle or the distance from the great circle, and you just kind of play with those three lengths, or the radius of the sphere, and you play with those three lengths. Next, we have the hemisphere. Now the hemisphere, over here, as you can imagine, it's basically the sphere cut in half. However, you have to add a circular base. Okay, a hemisphere is still a 3D figure, and so it's enclosed. You can't have a hole at the bottom. And so when you cut your sphere in half, you have to add on a lid of sorts. Okay, you have to add on the circular base here at the bottom. And that base is usually the area of the great circle, because you cut it in half, and the only circle that fits that exactly would be the great circle. All right? So now here are all of the equations and all the formulas for the circle and for the hemisphere. Small note, the hemisphere ones are not given in the textbook. Okay, so the two equations for hemispheres are not in your textbook, so please make sure you write those down especially, because you can't find them in the text. That said, as you write them down, pay attention to what you're writing down. Okay, notice how all of these equations, they only have the one piece. Okay, the only variable you have to really find is r squared, and then down here at volume, you have r cubed. So the only thing you need to find is r, and that's really helpful, and it's what makes these sphere problems simpler than some of the other problems, is because you're only looking for that one piece. Let's do some problems. I'm going to do the first one. So we have the surface area of a sphere, and the surface area is equal to 4 times pi r squared. Now my radius here is 7.1. It's going to be 4 times 7.1 squared pi. And you can plug this straight into the calculator, and that will give you the surface area is 201.64 pi. Don't forget your units. It is millimeters squared. All right, the video is going to pause. You guys do 1B. Small note, 22 is referring to the whole diameter. So make sure you're aware of that. Go ahead and do that one. And so here's your answer. Again, the 22 is referring to the diameter, not the radius, which means our radius is 11. And so when you plug that into your equation, you should have gotten 484 pi feet squared. All right, notice how I still have pi in both of my answers. Spheres are a circular figure, and pi always sticks around when you have circular figures. So leave pi as a symbol in your answer on these. Next one. Now in this one, we're going to be using the great circle. Okay, so in this problem, we are given the circumference of the great circle at 5 pi. So we want the surface area of the sphere, which means 4 pi r squared, but we have to deal with the great circle first. Now, the fact that you need to remember here is that the great circle has the same radius as the sphere. And so if we can find the radius of the great circle, then we have our missing radius for the sphere. So here I go. I've got the circumference, which is equal to 2 pi r, and I'm going to plug 5 pi in to my equation. 5 pi is equal to 2 pi r. When you divide 2 pi from both sides, you get 2.5 as your radius. And you can use decimals here because decimals are easier for the calculator. And now I'm going to take that and plug it straight on in. So I have 4 times 2.5 squared pi. And my surface area is 25 pi. Meters squared. Ta-da! So that's how you use the great circle. Now some of your problems might say here's the area of the great circle, find the volume or find the surface area of the sphere. Some of them might go backwards. They'll give you information on the sphere and say find the radius of the great circle or find the area of the great circle. Okay, but being able to go back and forth between great circle information and sphere information is something you should feel pretty comfortable with. Let's do another one. Now this one is volume, so make sure that you're aware of what equation you're using. We are given the circumference of the great circle, and we need to find the volume. So you guys actually go ahead and do this one first. The video is going to pause. When it plays again, you'll see the answer. And here's your answer. So again, we use the circumference of the great circle to find our radius, which was 9, and then you can plug it in. Now, 2 things I want to mention here. The 2 biggest errors at this point in the chapter is an equation error and a calculator error. So the equation error is usually just simply writing down the wrong equation or plugging it in wrong. So as you're writing down your equations and as you're solving your problems, pay special attention and make sure you're writing down the right one. Read the instructions, make sure it matches. Also, pay attention now. R is cubed on this one. Okay, that's another equation error. Make sure you have the things are cubed correctly or squared correctly, and you don't make any simple errors like that. Calculator errors, please make sure when you plug things in correctly, since we have fractions, that everything matches. Okay? You don't want anything that should be in the numerator to accidentally end up in the denominator. All that being said, make sure you write out your work as you do these. And that way, if you do have an error, you can go back and look at your paper and see where you messed up. But as you can probably see by now, the answer is 972 pi centimeters cubed. Again, don't forget to cube your units. We're doing volume now. All right, this problem. This problem is a bit of a challenge problem, so I'm going to pause the video and let you try to figure it out. But I'm going to give you one hint. So as we read it, the plane passes 3 centimeters from the center of the sphere with a radius of 5 centimeters. Find the area of the circle of intersection. So the question is asking you to find the area of the circle of intersection or of circle A. So the small circle up on top. Okay, this circle right here. Now the plane is passing 3 centimeters from the center, which means this length right here is 3. And the video is going to pause. You guys try to figure out the rest of it, see what you get. Okay, how'd you do? So the problem tells us that the radius of the sphere is 5 centimeters, which means in our little triangle over here, CB is 5 centimeters because CB is the radius of the sphere. B is kind of touching the part of the sphere that's coming out at you. Now, as I mentioned earlier, AC and AB are right because the segment that connects the two centers is perpendicular to that radius, which means you have a right triangle. And given that you have 3 and 5 as two of your sides, the other side has to be 4 because this is a 3, 4, 5 triangle. If that confused you or if you forgot about that, Pythagorean theorem is always a loyal friend when we have right triangles and you can easily solve for b squared, or for b. Once you found out that the radius was 4, you just plug that into the area formula, and then this is the area of the circle of intersection. So again, like I said on the last slide, it's just really important to be able to go from the great circle to the sphere itself, and this is another example of those problems where you have to juggle those pieces. All right, now composite figures. We've already kind of gone over composite figures in general, but we didn't actually solve for them. So this time around, we're going to solve for them. Now, if you're looking at these and you think you can do them, go ahead, pause the video, try them both out, see what you get, and then play them. I'm going to go ahead and walk through all the both problems. That way you can see what's going on. And here we go. Now, this first one is a cylinder and a prism. Okay, you can kind of see it's half a cylinder and a prism. So for the total area, I'm going to need to add the surface area of my prism plus the surface area of the cylinder. And then, as I mentioned last time we talked about this, notice how I have this overlap. Okay, and this overlap is actually one of my bases. It's actually part of my prism. So I'm going to need to subtract my overlap, but in this instance, I'm going to need to subtract the area of that one rectangle. Okay, so that's where I'm going with this. I have 3 pieces that I need to find. Let's start at the top. So the surface area of my prism, this equation is going to be perimeter times the height plus 2 times the area of the base. My perimeter, if I'm looking at my bottom, the very, very bottom of this shape, I'll outline it. There it is. So that's what I'm looking at as my base. That's going to be 6 plus 6 plus 15 plus 15. I'm going to get 42 from a perimeter here. The height is given to us. It's 4. And last but not least, my base. That's going to be 6 times 15 or 90. Okay, so those are all those pieces. So here we go. I got 42 times 4 plus 2 times 90. Plug that into the calculator and you get 348. Okay, I'm going to underline that because that's one of my big pieces that I'll need to keep track of. All right, next I have the surface area of the cylinder. Okay, this one's going to be 2 pi r times the height plus 2 times pi r squared. All right, my radius is going to be 3 because if this whole side right here is 6, that means that small piece is 3. And my height is going to be 15. Okay, because the height is what connects the two bases and that length is 15. I'm going to take these pieces and plug it in. So I have 2 times 3 times 15 pi plus 2 times 3 squared pi. Take all of that and plug it into the calculator. And you're going to get 108 pi. Now pause right here, because as I'm looking at my general equation, I see an error. Now, look at my picture itself. Okay, the picture itself is, as I said, the cylinder on the prism. But if you look carefully, it's not the full cylinder, it's half of the cylinder. So that means I'm going to need to take the surface area of my cylinder and divide it by 2. And so that's what I'm going to do over here. I'm going to take what I found and divide it by 2, and that gives me 54 pi as my second piece. Okay, and you can leave 54 pi, leave pi as a symbol for right now. We'll add it in a second, but there's no need to change it right at this section. All right, last but not least, I need the area of my overlap. Now my overlap is just that one singular rectangle. So I have area of the rectangle, which is 6 times 15, which is 90. And that's my third piece right there. So I'm going to take those pieces, I'm going to plug it into my equation. So I have 348 plus 54 pi, okay, minus 90. And you can literally just type that entire thing into the calculator. You would get at the end that the total area is equal to 427.6 inches squared. Now, as you can see, there's a lot of moving pieces, but if you're careful with your equations, you'll come out all right. When in doubt, label everything. Even if you got to put a box around your work, do something, but make it clear which piece you're working on, and that'll help keep your work organized. That being said, let's go on to the next one. Now, in this one, we have a cylinder on top and then a cone. So at least I know my total area is going to be, there we go, is going to be the area, surface area of the cylinder plus the surface area of the cone. I'm going to use N right there for cone. Now I've got to subtract my overlap, but let's pay attention to the pitch before we do anything. Here's my overlap. Now as I look at it, I see that it is not only the base of the cone, but it's also one of the bases of the cylinder. Okay, so the overlap actually fits nicely on 2 pieces, the base of the cone and the base of the cylinder. Therefore, this circle is technically counted twice. Once when we do the equation of the cylinder, and then once again when we do the equation of the cone. So here at the end, I'm going to have to subtract 2 times the area of that circle. Okay, 1 for each of the equations that it's in. So in this instance, it's not just the overlap, but it's 2 times the overlap because you've got those 2 pieces that match up perfectly. Okay, in our previous problem, the cylinder doesn't talk about that rectangle. All right, that rectangle is only a part of the prism. Now it lines up nicely with the cylinder, but the cylinder doesn't include it in its own equation. Whereas in this second example, that circle is in both equations, one for the cylinder, one for the cone. So we have to represent it in both. All right, the video is going to pause here. You guys do your best, and when the video plays again, you'll see the answer. And there's our answer. I ran out of room just a little bit, but you can still follow the work. So the surface area of the cylinder ended up being 252 pi. The surface area of the cone was 112 pi. And then the area of the circle was 49 pi. Put that all together in our total area equation, and you get 266 pi feet squared. Now, since all 3 of our pieces, the cone, the cylinder, and the circle, those are all 3 circular shapes, we're going to leave pi in our answer as a symbol because all the shapes involved are circular shapes. So if all the shapes involved have a circle, have pi, then pi is going to stick along for the whole answer. If, as in the case of the first one, the overall shape is not a circular shape, then just include pi as if it were a number. Okay, Last problem. You guys go ahead and do this one. Make sure you read the instructions. Good luck, and when the video plays again, you'll see the answer. And there's your final answer. Now, as a reminder, since it is volume, meaning all we want to know is how much space is on the inside, we don't need to subtract any kind of overlap, because by definition, the overlap is on the outside and volume only cares with the inside. So that's why in this problem you can just add your two volume totals together and then get your answer. Make sure you pay attention to the instructions when and where to round, as well as your units. Volume is units cubed. Alright, that's all for this video. If you have any questions, as always, make sure you write it down, and I'll see you next time.